Welcome to Lecture 4, 2D Particle Equilibrium. In this lecture, we will revisit the definition of a particle as well as the definition of equilibrium. We'll get our first exposure to free body diagrams, and then we will look at equilibrium in 2 dimensions. A particle is an object or a body that has mass but can be modeled as a single point in space. Doing so simplifies analysis in that we're not concerned with the geometry of the object or body that we've idealized as a particle. A particle is said to be in equilibrium when the resultant of all the forces acting on the particle is zero, which is to say that Newton's first law is satisfied. We state that mathematically by the equation here, which should look familiar. And note that we generally use the term equilibrium to mean that the object is at rest. But equilibrium implies that the object is not accelerating, which means that the object's velocity is constant. So a velocity of 0 or at rest satisfies that condition. But remember that a non-zero constant velocity also satisfies that condition. Before we move on to discussing equilibrium in 2 dimensions, we need to look at free body diagrams. A free body diagram shows a particular particle of interest and all of the forces acting on it. And we use them to help visualize how the forces in the given situation act, to help us write the equations of equilibrium for that situation, and to document our assumptions in our work, not only for ourselves, but for others who might be reviewing it or using it in the future. Free body diagrams are indispensable in the study of engineering mechanics. We construct a free body diagram using a 3-step process. First, we sketch the body by showing it cut free from its surroundings. Second, we show all forces that act on the particle. This includes active forces that tend to move the body, such as the body's weight, and reactive forces that tend to resist movement. Third, we identify each force. We label all known forces with their magnitudes and directions, and we don't always know both magnitude and direction, and label unknown forces with appropriate variables. Let's look at a couple of free body diagram examples. This first example, we have 4 struts that are connected together at point O by a pin and loaded as shown. And let's assume that we're asked to draw a free body diagram of the pin that's connecting these 4 struts together. So we'll start by creating a new diagram. We'll draw the pin O, the pin at O, as a particle. We're assuming we're not concerned with the geometry of the pin. And then we'll cut free the pin from its surroundings by removing each of the struts and replacing the strut on the free body diagram by the force that it is contributing to the pin. So let's do that one at a time. We'll start with the 7 kilonewton force. So we show that, and I know I've pre-drawn it here, so Assume that the we just have the pin at O shown as a dot here at the origin. So then for the 7 kilonewton force, we would draw in the force, mark it as 7 kilonewtons because we're given the magnitude, and show the direction, which is given by the slope triangle. So we've removed that that strut that has 7 kilonewtons applied to it from pin O and replaced it by the force that it was contributing or applying to pin O. Now we'll do the same thing with the 5 kilonewton force. We'll draw in a force of 5 kilonewtons. And we are told that it acts at a 30-degree angle with respect to the negative x-axis there. So now we've removed these struts. Let's look at the strut that has F2 associated with it. We draw in another force here. Now the magnitude of this force is unknown, and we'll just call it F sub 2, but its direction is known, and we just show that as the 70 degrees from the y-axis. So this strut has been accounted for. The last strut is going to have 2 unknowns. We don't know its magnitude or its direction. So we draw that in and make sure we mark it with F sub 1, which is a variable, just like F sub 2 was, and theta, which is the direction of F sub 1 with respect to the x-axis. Okay, so we've cut the pin at O free from its environment and created a free body diagram of the pin at O. Now, is the free body diagram complete? Have we missed anything? So technically speaking, the pin at O, we've modeled it as a particle. We're saying that particles don't have any geometry. They're just a point in space, but they have mass. So what about the mass of O, more specifically the weight of O, which is the gravitational force? So we could show the weight of O as the mass of O times the acceleration due to gravity. But in problems like this, look at the magnitude of the forces that are being applied to this thing. 7 kilonewtons, 5 kilonewtons. And in this problem, we would most likely assume that the weight of the pin itself is insignificant when compared with the magnitudes of the forces existing in the problem. So we would just ignore the weight of the pin in this problem and not show it on the free body diagram. Let's look at a second example here of a free body diagram. And in this example, we should get a little better feel for what we mean by cut free the body or particle from its surroundings. So here we have a 40 kilogram mass suspended from a ring at A that's held in place by 2 cables. So assuming we're going to draw a free body diagram of the ring A, which we can model as a particle. I've drawn it as a ring. It doesn't matter. That's your choice how you want to show it in your free body diagram, but we're considering it to be a particle. We draw that ring, that particle, and then we proceed to cut away each of the attachments, the cables, one at a time, and replace what's been cut away by the force it was applying to the ring. So let's start by cutting away the 40 kilogram mass first, and just assume I do a cut here and the 40 kilogram mass is no longer attached to the ring. Now, what force was that 40 kilogram mass applying to the ring? Well, we know that the acceleration due to gravity is pulling that 40, trying to pull that 40 kilogram mass to the center of the Earth. And we've said previously that that is known as weight. The force, we show that as a force known as the weight, and that weight is equal to mg. So we'll draw a force on the ring in the negative y direction, and the magnitude of that force is going to be m, which is 40 kilograms, times g, which is 9.81 meters per second squared, and those units are what we call newtons. So that force has known, that weight force has known magnitude and direction. Let's cut away this cable here that's coming from D and show it on the free body diagram. So that would be shown as a force acting along the negative x-axis. So we know its direction, but we don't know its magnitude, so we'll label that as the variable f sub d. And then lastly, we'll cut away the cable that's coming from B. Draw that in our free body diagram. We don't know the magnitude, but we do know the direction. And again, in this example, we're going to ignore the weight of the ring, as we're assuming it's insignificant compared to the other forces involved here. Let's look at two types of connections frequently encountered in particle equilibrium problems. First one will be the spring. A spring will exert a force of magnitude F that is equal to its spring constant times the amount of stretch or compression. So assume we have a spring attached to particle A here. If the spring is being stretched, we would show the force as pulling on A, and the magnitude of the force would be Ks. If the spring was in compression, we would show it pushing on particle A with a magnitude of Ks. The second type of connection that we see frequently is cables and pulleys. For any continuous length of cable, the tension in the cable is always going to be the same everywhere along the cable. cables can support only tension or pulling. You can't have compression in a cable. You can't push a cable. You can only pull it. And the force exerted by the cable acts in the direction of the cable. Now, assumptions that we're making when we make these statements are that the cable has negligible weight and any pulleys that the cable travels over are frictionless. Coming back to particle equilibrium, for coplanar force systems where equilibrium exists, the sum of the forces has to equal zero, Newton's first law. So for any particle in that system, the sum of the forces on that particle will equal zero. Now we can write this side of the equation in its Cartesian form here. And if this equation is true, then it can't be true without both of these being zero. Might have to think about that a little bit. And that allows us to write these two equations here, scalar equations, which says that the sum of the magnitudes of the forces in the x direction on the particle is equal to zero. And the sum of the magnitudes of the forces in the y direction is equal to zero. Now we'll be using these two equations to solve for up to two unknowns in the coplanar force system problems that we'll be doing.